So this problem is going back to that work that we did in previous weeks where we're doing it all without calculator. So remember, the first thing I do is I figure out what 10% is of my number. So 10% of 8,000, remember that moves the decimal over one place. So 10% is 800. Now if I want to know what 15% is, that means I also then need to figure out what 5% is.
Is that a time sign?
So 5%, that's going to be half of 10%, right? So that's going to be 400. So I just took my 10% and I cut it in half. So then if I want to know what 15% is going to be, I take my 800 and I add the 400. So then that just gives me 1,200. So that, remember though, is what the 15% is. That tells me what it went up by. The question is, how much is it actually worth now? And so we still have to finally, to get our final answer, I got to add the 8,000 to the 1,200, which gives me then $9,200 as my final answer. All right, so for attacking this one can be a little deceptive because we see we go down by 10% and then we go up 10%, so we assume that it should end where it starts, but it doesn't. The answer is not going to be 300 here. So first up, I want to figure out what the 10% discount is. So the 10% discount, so that's going to be 10% of 300, so that's going to be 30. So that means that the actual price, that is the actual thing that they're charging us, is going to be 270 because I do 300 minus 30. Now that is what I pay tax on. I don't pay tax on the 300, I pay tax on the 270. So the 10% tax, 10% of 270 is 27. And so, if we then want to know the actual cost, that is the original price plus tax, we do 270 plus 27, which gives us 297.
Wait,
so notice it does not equal 300, because the 10% tax is being applied to a smaller number than the original 10% was. All right, so this is going to be kind of the theme of the day today, is I'm going to be giving you a table and asking you to write the equation of the function that's described by it. Typically, we're going the other way. Typically, I give you an equation, we just plug in values. But one of the things I want to do here is give you sets of numbers and have you recognize certain patterns. Because we've seen a number of different function types this year. And all of them that we're going to be looking at here, except for one, go with one of those function types that we've already spent a lot of time with. And so if we already know like what these graphs look like and all that, we should know what the number trends are as well. All right, so in this one, as I look at this data, some of the things that jump out to me and that are going to tell me how to approach it are, first of all, as I look down the x's here, they're all going up by ones. So it's nice and straightforward on the x side. Most of them tend to be. When it's not, that's a big flag to us that something else is happening. We'll talk about that when we see it. Now, as I take a look at the y's that respond to the x's, are those going up by the same amount every time? In other words, 4 to 6.
4 to 6? Hold on.
I'm sorry, why did I say 4 to 6?
Wait, hold on.
9 to 4.
It's Friday, we're all tired.
9 to 4, that's 5, right? 4 to 1, that's 3. 1 to 0, that's 1. Is it going up by the same amount?
No.
No, definitely not. And so that already ruled out any of our graphs that are straight. Because if it was a straight line on our graph, it would have to be going up by the same amount as we go down our y's. All right, so that actually narrows it down to actually just two different graph types. What am I doing to x to get this y value? Yeah, it's multiplying it by itself. And when we say multiplying by itself, what's another way to say multiplying something by itself? Squaring it. So in this case, our equation is y equals x squared, which is one of our nonlinear. The linear ones, the ones where it's going up by the same amount each time, are either y equals x, or technically it's not linear, but it acts like it's linear on both sides, is the absolute value of x. Those are the ones that will go up by the same amount every time. Now, as you do these problems, if you find one that just totally stumps you, one way to get around it is you can actually either make or visualize the graph by saying that this table of values really just represents a set of points, like -3, 9, -2, 4, -1, 1. And all of those just represent points. And so when you get totally stumped on one of these, you can always resort to making a graph, because when you see that graph, you recognize that shape, because we know that this U-shaped graph is the quadratic graph, the x squared type. All right, next table. All right, so again, I start the same way by looking down my x's. Notice they're all going up by 1 each time. Okay, so that's like normal, so nothing's weird there. I look down my y's. And what I want to know with my y's is it going up by the same amount each time? And so let's check that out. -3 to -1, that's a total distance traveled of 2. -1 to 1 is 2. 1 to 3 is 2. This is looking good. Is it 2 every single time?
Yes.
Yes, it is. So that tells me that this thing is linear. It's a straight line, which means either my equation is just y equals x and some modification of that, or the absolute value of x. Now, how do we know which? Well, remember the absolute value graph is a V shape. It bounces at some point. So it'll be like going down by the same amount, and then all of a sudden it'll start going up by that amount. If it's just a line, it's always going to be going by the same amount. And it's never going to have that kind of bounce effect in it. All right, so in this case, do our y values ever bounce like that? No, because it was always actually increasing by 2 each time I went down. Okay, so that tells me that it's going to be some variation then of just y equals x. All right, now how do we know what the details are within that? Well, again, you can make a graph if you want to. In this case, -3, 3, -2, 1. And I can just keep seeing each of those points, and that might help you to see how we actually get our graph there. The other thing that I look for when I know that it's going to be a line of some sort is I look to see where 0 is. When x is 0, what's y? In this case, it's 3. Well, that means that I have to have a +3 sitting on the end, because normally at 0, it's at 0. And so this tells me the graph has moved up 3. And so I do a +3. Notice, though, that means literally, like I took, this is supposed to be 0 here normally, so I added 3 to the normal value. Okay, and what's it going up by each time again?
2.
No.
So that means it's 2x plus 3. And so this is actually our equation. So when you see linear equations like this, that's kind of the general rule. The value at 0 is whatever you add or subtract onto the end.
I knew it.
Whatever the spacing is, that's what we multiply by. And so we multiply x by whatever we're going up by. So kind of different ways to see it, but there's other patterns and other ways to kind of process it through. All right, next table. All right, so as I take a look at this one, again, I start by taking a look down my x's. Are my x's going up by the same amount each time?
Yes.
Yes. Okay, so that's going to make our lives hopefully a little bit easier. My y's, are they going up by the same amount each time?
Yes.
Yes, they are. Okay, so that tells me this is one of those that involves a straight line. As I look at my y values, do they ever have that kind of bounce effect that we'd expect from absolute value?
No.
No. Because every single time I go from one number to the next, 5 to 4, it's going down 1. And every single one of these continues going down 1. Okay, so that tells me I can go ahead and I can write my equation then. So it's going to be y equals, and it's just got an x in it. Okay, what number is added or subtracted after the x? Well, the way to know that, remember, is when x is 0, y is normally 0. Instead of 0, it's at 5. What do I do to 0 to get 5? I add 5. So it's got to be a plus 5 hanging on the end.
Yay.
Okay, although this equation wouldn't actually give us that data. It'd give me the 5, but x plus 5 would then tell me the next number would be 6. This would be going up instead of going down.
It's a negative.
So, yes, I got to make that a negative x plus 5.
Wait.
All right, so in this problem, we got a new set of data. I start the same way. I look down the x's and I say, okay, is that one going up by the same thing every time?
Yeah. No.
Yeah, no.
No.
No, it's not. So this is actually kind of then a red flag for us. This tells us that something very specific is happening.
I know
We have one particular graph where when we go and plot the points, we don't go over 1 every single time. Instead, I would go over 1, and then I'd go over 4, and then I'd go over 9. Which graph am I making when I do that?
square root.
Square root, yeah. So we know that, right? Let's see if that actually matches up here. What's the square root of 0?
0.
0, okay, so that checks out. What's the square root of 1?
1.
1, okay. What's the square root of 4?
5.
Okay, so this is checking out, right? Every single one of these, square root of 9 is 3, square root of 16 is 4, square root of 25 is 5, and square root of 36 is 6. So then, our equation then is y equals just the square root of x. No modifications or anything else done to it. Alright, so for this table, again, I look down my x's, and I see, am I going up by the same thing every time? So like from negative 3 to negative 2, that's going by 1. From negative 2 up to 1, that's by 3. 1 to 6, that's 5. Okay, so we're not going up by the same thing every time.
You're going up.
Whenever I see that, where I see that I'm going up by something different every time, that makes me think of square root. But what's the square root of negative 3? There isn't one.
There isn't.
Yeah, we can't do the square root of a negative. So how can we possibly get 0?
Can't.
Well, we can actually tweak it a little bit. Let's see how we would approach it. What we can do with that then. So
No.
let's take a look then down our y column here. The square root of what is 0? 0. So if this were a 0, I could get 0. The square root of what is 1? The square root of 1
There is none.
is 1. The square root of what is 2?
I don't keep that. Wait, is it 2? 0.
Square root of 4 is 2. Okay. Square root of what is 3? 9. So this is really going through that whole set of all those numbers that I normally would take the square root of to get that.
But then what's with the
So now,
and then it's minus.
now compare that to our actual x values here.
It's minus 3.
So
Of x plus 3.
if it was 0, it would work. So what do I do to 0 to get negative 3? What do I do to 1 to get negative 2? Well, in fact, what do I do to every single one of these to get that value?
Minus 3.
We subtract 3. And so I take whatever the square root of x is, and I'm going to have to subtract 3. But what am I subtracting the 3 from? The x, yeah. That x.
Do you add 3?
Okay, so I got the 3. So let's see if that works then. Okay, so if I do x minus 3, so negative 3 minus 3 is... Wait, that's negative 6. Oh, that's why I have to actually add the 3. Because if I do negative 3 plus 3, that gives me the 0 then. You know how when we make the graphs of these, the plus 3 actually moves it left? It's kind of backwards from what you'd think. It's the exact same effect here. And we can actually see how that ends up happening in the table. So I have to do plus 3 to it to make it into the 0, the 1, the 4, the 9, the things I can actually take the square root of. So there's your equation. Y equals the square root of x plus 3. Make sure the plus 3 is inside the radical. All right, so again, we take a look at the problem the same way. I always start by taking a look down my x's. Are my x's going up by the same amount each time here? No. So that already tells me, that makes me think of square roots. So I'm going to see, can I make this work with a square root function? All right, So normally to get the 0 over here, I'd have to take the square root of 0. Normally to get the 1, I'd have to take the square root of 1. Normally to get the 2, I'd have to take the square root of 4. Basically, I'm going back to that same pattern that we normally have and seeing, can I turn those numbers into the given x values over here? Well, we can. What am I doing to them? It looks like adding 5. Or maybe it's easier to say, looking from there to there, I'm subtracting 5. On every single one of them, they're 5 apart. So that tells me that it's going to be the square root of x minus 5. And that's how I'm getting my y value. Now, what if that's tough for you to wrap your head around? Because you know what? I would expect it to be kind of tough for you to wrap your head around. So another way that we can approach it. Remember that we can sketch a graph of these to kind of visualize what's happening. If I plotted a few of these points, I can only really plot a few based on the graph here. 5, 0, 6, 1, 9, 2. Notice that's telling me here that the whole graph was shifted to the right 5 units. And the general shape is telling me square root. So I could always fall back to plotting some of these points and seeing what it's doing. The only thing is, though, that I don't want you relying on that. I don't want you having to take every single table of values and having to plot all the points from it, because it's a pain. And it's really not necessary, and it's not where I'm wanting to train your brain anyway at this point, because I'm wanting to train your brain to start thinking about what's different about a square root versus a squared graph versus something linear. What are some of those differences along the way? All right, so here's a new table. And again, I start the same way. I'm going to look down my x's. Are my x's all going up by the same amount each time?
Yes.
Yes, they are. It looks like they're all going up by 1s. So that already tells me, okay, we must not be dealing with square root here, because square root, if you go up by 1s, the whole thing, it gets really messy in the decimals on the right-hand side. That ain't happening. All right, so then, now I look at my y's. Are my y's all going up by the same amount each time?
Well, it goes down by 1 and then up.
It's kind of a yes and no, isn't it? Yeah.
Well, they go down by 1 and then up.
Because
so that'd be the bounce.
3 to 2, that's -1.
They go down by 1.
-1, -1. But then notice, I go up 1. Up 1. That's that bounce that we've been talking about. Yeah. And so since that has that bounce in it, but otherwise it's going up by the same amount each time, it tells me it's straight, but that it's going to have some sort of a change of direction. In other words, it is a V-shaped graph. And so I know in order to get a V-shaped graph, it's the absolute value of x involved. And this one has no actual funky shifts or anything like that in it. It's only just the absolute value. It's our parent function, specifically speaking. And so there's your equation. Y equals the absolute value of x. Okay, next table. And with each of these, if you already know what it is, super easy, then go ahead and write down the equation. Otherwise, write down the table so you can then write down the equation as we discuss it. All right, so to write this equation, again, I start by looking down my x's. Are they all going up by the same amount each time?
Yes.
Yes. Okay, so that pretty much rules out square root. All right, already making progress. As I look down my y's, are they going up by the same amount each time?
No.
Yes.
Kind of,
Yes, and
right? Because I'm going down 1, down 1, down 1, but then I'm going up 1, up 1, up 1, which tells me that yes, it's basically going up by the same amount, but that it does make the bounce, which tells me that it's going to be absolute value. So I know I'm going to have absolute value of x involved in this. But notice it's not just going to be the absolute value of x as my final answer. Because if I were doing that, I would have a 0 at 0, and these would actually be my numbers. Well, what am I doing to those numbers to get my y values?
If you use 7 to get to the 7, but
Yeah, it would be plus 7. Yeah, so we're adding 7. Now, am I adding 7 before I take the absolute value? That can sometimes be a tricky part to think about. If that one throws you off, think about this number right here. When x is 0, it still gives us 7. So that's like it's been moved up. And so that's an extra little indicator, going back to stuff we already know, that the plus 7 needs to go on the end. All right, so then that is your equation there. And again, you can visualize it graphically if you want to, and if that helps you to kind of see what's going on, because we know the graphs so well. We spent so much time dealing with those graphs.
Oh, I see.
All right, so for this one then, I look down my x's. Are my x's going up by ones?
Yep.
Yep, they're going up by the same thing every time. How about my y's? Are they going up by the same thing every time? No. It looks like it at first because it's down 1, and then it's up 1. So at least those are a difference of 1, but then that's 3, and that's 5. Yeah, we're definitely not going up by the same amount each time. So that means if I were graphing this, they would have no straight lines in it. And my x's are all going up by the same amount, so it's not square root. So that tells me it must involve x squared. Okay, so now that I know my target is an x squared function, let's think about what it would normally be. Well, what's negative 3 squared? That would be 9. Negative 2 squared would be 4. Negative 1 squared is 1, 0, 1, 4, 9. Is there a way that I can turn each of these y values into those numbers?
We'd have to add
Let's see, that's like plus 8, plus 4, plus 0, minus 4. No, that's not working for us. Okay, so if that's not working for us to change the y's, let's look at the x's. What squared equals 1? That'd be 1. What squared equals 0? What squared equals 1? What squared equals 4? What squared equals 9? And so on. Okay. How's this going to work? Well, actually, you know, if I remember that a negative 1 squared also equals 1, then that can work. Because notice, 2 apart, 2 apart, 2 apart, 2 apart. They're all 2 apart going down your x's. Now, again, this is one of those that's probably about the trickiest that you're going to see. Let's take a moment, plot the points. Negative 3, 1, negative 2, 0, negative 1, 1, 0, 4, 1, 9. That's the last one I can fit on my dim little grid here. I'm seeing a quadratic. Notice zeros right here. I made it dim so we weren't focusing on it. So I'm seeing a quadratic because I'm seeing a U-shaped graph. Notice how it's been shifted. It's been shifted left 2. So is that my equation? Not quite, right?
Okay, I was about to say.
That'd be right 2. There's our left 2.
Oh.
So notice, what am I doing to the x's to get my new x's? I'm adding 2 to go from my original x to my new x. Now again, this is about as hard as it'll get, right? So when it gets really hard, if you're just feeling totally stumped, that's when you can actually resort to plotting the points. And hopefully the more you do it, the less you'll need to do it, because you'll see more and more how to actually make those things connect up.